Hello students. Today I will be teaching you the first chapter of physics, that is electricity and its effect. And this is the first lecture of this chapter. I have prepared PowerPoint slides. As you all know that due to the lockdown, we are unable to provide the classes in school. So I have tried my level best to make a good video for you all. Before going into the topic, I would like to show you the topic which I will cover in this first lecture. So this is the outline. Here I have uh, written the topics which I will discuss in the first lecture, that is introduction. After that, electricity, the most convenient form of energy, and finally electric charge and current. So these are the three topics which I will discuss in the first lecture. So moving to the introduction, ancient Greeks discovered electric and magnetic phenomenon in early 700 BC, in which they observed that when a small piece of amber is rubbed, gets electrified and attracts small pieces of straw and feathers. The word electric itself is derived from the Greek word for amber called electron, spelled Eleckton, electron. Later in 1600 AD, William Gilbert discovered for the first time that electrification phenomenon was not just limited to amber, but it is a general phenomenon. That means in earlier time, the Greek people, when discovered the peculiar property of an amber, when rubbed by a suitable material, gets electrified and it start attracting pieces of straw and feathers. And the people used to think that it is the only amber which has such property, that is of getting electrified when rubbed. But this theory got disproved by William Gilbert in 1600 AD, when he concluded that electrification phenomenon was not just limited to amber. He gave a general idea that electrification phenomena is a general process rather than being a specific property of amber. Moving to the next slides of introduction. Similarly, in 1785 AD, Charles Coulomb, a very renowned scientist, found that the inverse square law is applicable to the force acting between two charged particles, which I have illustrated in figure 1. We can see that this is particle A having charge Q1 represented by A, and this is particle B represented by B having charge Q2. Both these particles are separated by a distance r represented by small r. So according to the inverse square law, the electric force which is acting between the two charged body is inversely proportional to the square of the distance between them. This is similarly as the inverse square law which is applicable in case of gravitational force. I hope that all of you have learned gravitational chapter in class 9, where the force acting between the two masses, mass m1 and m2, is inversely proportional to the square of the distance between them. So this is merely called inverse square law. So moving to the next topic, that is electricity, the most convenient form of energy. Electricity is the most convenient form of energy. The reason behind that is, once the electricity is generated, it can be easily transmitted and supplied to the remote areas which is very far away from the place of generation with minimum loss. That means when we produce electricity by any means, be it either nuclear power by nuclear power plant or a hydropower plant or anything like thermal power plant. So once the electricity is generated, it can be easily transmitted to the remote locations. And while the transmission, the loss is very negligible. We use electricity for various purposes also, like for domestic lighting and heating purpose, for running the machines and equipments in industries, in schools, hospital, roads, streets, etc. Obviously, questions that might crop in your mind are what is electricity, what makes the electricity flow, how is electricity generated and transmitted, and so on. So we move to the next topic, which will give the answer to your questions, that is electric charge and current. So I have explained this flow of charge in figure 2. This is particle A, represented by capital A, having potential, electric potential V1, which is connected to particle B having potential V2 by a metallic wire, where the condition is given that V1 is greater than V2. This is just an example that I want to show the both potentials are not equal and V1 is greater than V2, and this is essential so that the current will flow from higher potential to the lower potential. Charge flow from one body to another body until the potential becomes equal, that is V1 equals V2. The flow of electric charge from a body to another body through a conductor is called electric current. So moving to the definition of electric current, the quantity of electric charge flowing through a conductor in 1 second is called current. If Q is the charge which flows through a conductor in time t, then mathematically current, which is represented by I, is equal to charge represented by capital Q divided by time, which is represented by small t. And electric charge is neither a scalar nor a vector quantity. As we all know that scalar quantity have magnitude and vector quantity has magnitude as well as direction. Now the question arises, what kind of quantity is electric current? If it is neither scalar nor vector, then what kind of quantity it is? So this is the first question. I have given here the assignment number. This is the assignment 1, and you have to find the answer. Moving to the next topic, units of current. So we have current I equals charge Q divided by time t. The SI unit of charge is coulomb. It is represented by capital C, and that of time is second, small s. So the SI unit of current is equal to 1 coulomb by 1 second, which is also represented by 1 coulomb per second. So moving to the next slide, and coulomb per second is also called ampere, which is generally denoted by letter A. So the SI unit of current I is ampere. So these are some of the smaller units of current, that is milliampere, microampere and nanoampere. So milliampere is 10 raised to the power minus 3 ampere. Microampere means 10 raised to the power minus 6 ampere, and nanoampere means 10 raised to the power minus 9 ampere. So now we move to the last slide of this lecture, and the topic is the definition of ampere. So now we know that ampere is the unit of electric current. So what will be the definition of ampere, or let me say that what will be the definition of 1 ampere? So from the formula we have already know that current equals charge per unit time, and if the charge q is 1 coulomb and time t is 1 second, then the current I will be 1 coulomb per 1 second, which is represented by 1 ampere. So the overall definition will be when 1 coulomb of charge flows through a conductor in 1 second, then the current passing through the conductor is 1 ampere. In other words, we can also say that the current is the amount of charge passing through a conductor in a unit time. So this is the end of the first lecture, and in second lecture we will be discussing electric potential and potential difference.